Okay, so this lecture is on the derivation of the half-life formulas, which you will definitely need in certain AP problems. Um, let's start with the first, okay, integrated rate law equation, which I uh, derived for you in another lecture, and it's AT, concentration of A of some time, equals A minus KT. Of course, it's A naught. Okay, first thing we're going to do for this zero order, okay, the derivation of half-life, and we're going to do this for all of them, is that we're going to say that 1/2 concentration of A naught is equal to concentration of A to some time. That's what half-life is. It's the amount of time it takes for half of your initial concentration to get to that point. So it's the amount of time it takes for half of your original to achieve that concentration. So we're going to plug that in, okay? So we're going to use this value that's going to plug in for A of t, okay? And what we're going to get is 1/2 right above, because we're just plugging in for this guy right here. 1/2 of the A's original concentration equals A original minus KT. Okay, now just a little simplification. All right, so let's take a negative A of 0 to both sides. And what we get is 1/2 A0 minus A equals negative KT. And we can see that 1/2 of X, or A, minus a whole one gives us a negative 1/2 of A0, right? I'm doing a half minus a whole gives us a negative half equals negative KT. We can multiply both sides by -1, so we get that 1/2 A of 0 equals negative KT. And of course, I'm going to divide by both sides by K. Hope that'd be positive because I got rid of the negative. All right, so both sides by K. And of course, what I get is and this 2, of course, is the same thing as 1/2 here. I get the concentration of A at initial concentration, that's A naught, over 2 times K equals this time period, which I'm going to put to the 1/2. Okay, so the half-life, the amount of time it takes for a zero-order reaction to cut in half from initial concentration, is related by this expression. Okay, and this is what it is. Now notice very simply that if you know the half-life and if it's first order, okay, and you know its initial concentration, you can solve for K, but more importantly, the half-life is dependent upon the concentration. Change the concentration, you change the half-life. If you notice, that's not how radioactive elements work. Radioactive elements, okay, their half-life stays actually constant because it does not involve the concentration. So this is zero order, okay, half-life formula. Let's go on to first order. Okay, and in first order, we have our integrated equation to be, and now I did not do this one. I'm going to, if I haven't already, create another video to show the derivation of these two. I did derive this, but in any case, the formula that we use from the same work that we did to come to this point for zero order is here. So ln of concentration of A of some time period, minus the ln of A initial concentration equals negative KT. All right, and what we're going to get here is we're going to do the same kind of fill in here. 1/2 of A initial is equal to the concentration of A to some time period. So when we plug that in, okay, we plug that in right here, and what we get is we get the ln of 1/2 A to some time, in this case, some time period, 1 half of A initial, I'm sorry, minus the ln of A naught equals, again, negative KT, put a little half here since we're trying to find that half-life. Okay, so we're going to divide by K. All right, I can divide by negative K if I like. So divide by negative K to both sides. And of course, K's cancel. Okay, and when I do that, what I'm going to get is the ln of A naught over 1 half of A0 times K equals T to the half. Now, by dividing by K, the K's in the bottom, as we talked about, and we know that when these are really exponents, right, base C exponents, and you know when you subtract them, you certainly are dividing. And now you may say, well, why is this one on the bottom? Well, because we had this negative sign that basically flips the inverse, right? We divided by a negative sign here, negative K to both sides. Okay, so this makes a negative, okay, makes really, if we take this negative away, put it here, the negative of this is going to be the inverse, so it becomes this ln of A minus over here. So we might put the negative side, made this an inverse to create that scenario. So in any case, very simply, at this point, we are going to now cancel A of 0. With that goes by the wayside. And the ln of 1 over 2 is the same thing as the ln of 2 over K equals that half-life. And that is our first order derivation of half-life. And that is something they do not give you in terms of a formula. They expect you to be able to derive that and use that. But it's a ln of 2 over K, something that you may want to memorize. I'm not big on that, but you should be able to do this derivation if need be. But notice something very important. This is a really important concept here. That in the half-life, okay, relationship of K and some numbers here, this equation, it is not at all dependent upon the concentration of initial concentration of your reactant. The initial concentration of your reactant is not important in determining the half-life here. So if we think about radioactive decay, for example, uranium-238, it has an atomic number of 92, and it undergoes alpha decay, becomes it gives off a helium nucleus, mass of 4, 2 protons, 2 neutrons, and it naturally transmutates to thorium, which is atomic number 90, so it loses 2 protons, and its atomic mass goes down by 4 because of the 2 neutrons that's also emitted, so we got 234. This radioactive decay we talked about last year, okay, is first order. Just by itself, it gives off a particle. And we've also learned is that we can't decrease, increase, or change the half-life period it takes for it to decay into more stable and safer compounds. Okay, we're totally basically up in the air in terms of how to handle this, but we know that increasing temperature, increasing changing of reactants do not affect, okay, nothing affects the half-life. It's stable and it's constant, and it's because it's not based on any concentrations. It's independent of the concentrations, much like or much against or much different than a zero order, and as we'll see shortly, a second order is dependent also on concentrations. So this is very important. This is why this one is the one it's always picked on. Okay? So let's continue with deriving the second order half-life. And we're going to start with our definition, 1 over A to some time period equals positive KT plus 1 over A naught. We're going to make our substitution here. A of T, of course, is equal to 1/2 A naught. All right, so we got 1 over that equals KT plus 1 over A naught. Okay, now I am going to multiply both sides by A naught, initial concentration. Okay, initial concentration takes that away. Okay, notice 1 over half is going to be 2, and that's KT. But multiplying this through, this cancels, leaves me a 1 here, plus 1. But I'm also multiplying, distributing throughout. This is a plus, not a multiply. So I'm multiplying through here and here mathematically. So that gives me the A naught expression over here. Simplifying, our T of course is to the 1/2, as I should have wrote, but we get the idea here. We're going to subtract our 1, okay? We get, of course, we get our 1 equals, bring our K, T to the 1/2, A initial concentration, and now we just have some simplification solving for T to the 1/2 here. Okay, everything else goes to the bottom, and we get T to the 1/2 for second order is equal to 1 over K times the concentration of A naught. And that is our second order. Notice its half-life, the amount of time it takes for half of its original concentration to have, okay, is dependent upon the concentration, but 1 over the concentration times K. If you look at our other derivations, okay, first order, it was the concentration original over 2 times K was dependent upon that half-life, whereas first order does not depend on the concentration. Okay, this is the one they love to pick on. Okay, now if we looked at the graphs of these, we can see some interesting scenarios. Okay, so we're looking at half-lives for a zero-order reaction. Notice that first half-life, going from 10 to 20, took, I don't know, some number of minutes here between 20. Why did I not make something nice? But it looks like 32 or something, 32.5. And the second half-life, the second halving, is changing. So the half-life is dependent upon the concentration. So as the concentration decreases, the half-life also decreases. There's less of it. That's zero order. Okay. Our most famous one is first order. And if you notice, the half-life is consistent all the way through. Again, why are we picking a weird half-life? But this number here, this segment of line here, looks like 7 seconds is my half-life, stays constant. So 7 times 3 is 21, and all our half-life problems that we've been using with radioactive substances occur because of this constant. Okay, and we know that because of the half-life, which is equal to, well, let's go back to our derivation. We'll see that's not dependent upon concentration, so you can see that that half-life is constant. And of course, the second order, more steeper exponential, its half-life decreases with concentration. Okay, why would it decrease? Okay, I'm sorry, increases with decreasing concentration. So the half-life gets bigger as the concentration decreases, and of course all of that has to do with, okay, the derivation here. Okay, if you notice second order, okay, our derivation here, so as this decreases, okay, the half-life gets bigger, like the graph shows. And for the zero order, as this decreases, the half-life decreases. But most important, first order, there is no change in the half-life because the concentration is not built into the formula as we derived.